works for this trade-off. All right, moving on. Okay, now we're here, the meat of it all. What we're going to do is linear predictive coding analysis. That is fundamentally what formants are. Is they're coefficients that, or sorry, not coefficients, but their values extracted from constructing a large polynomial. Now, what do I mean by that? So when we're trying to construct a polynomial of this form to represent our signal here, our signal x of n. Now, no, I noticed that I went discrete again. The reason why I'm using a discrete value is though we just spent the last page constructing continuous signal, we're discrete again simply because the computer, while it has values for across time, it will use discrete values to compute the formants. That alongside the fact that discrete numbers are usually writing these discrete equations is usually a little easier to conceptualize. Anyways, so what we're going to do is we're trying to approximate our signal with a linear combination of time-shifted versions of our signal. And what we're going to do is we're going to multiply our linear combination, right, our time-shifted version of our signal here by a coefficient. Each one is going to get its own unique coefficient determined by an autocorrelation. So the zeroth coefficient is going to be determined by just basically an autocorrelation of this will be the highest coefficient. It'll be determined by just the dot product of the function with itself. And the first coefficient is going to be determined by a dot product between a function and a time-shifted version of itself. What is the time shift? Well, k in this case equals 1. And anyways, when we want to get 5 formants, want to create that 5 to 6 formants, we want to create a polynomial that is 10 to 11 terms large. And that's what we mean when we say prediction order. That is this value p up here. That is how many coefficients that we are going to get to reconstruct our function with time-shifted versions of our original function. Anyways, so what's different about the particular kind of linear predictive coding analysis that Praat uses is something called the Berg algorithm. And what that is exactly is similar to normal linear predictive coding analysis. You'll get forward prediction error and backwards prediction error. Forwards prediction error is just, okay, if we are using previous samples, how well can we predict future samples? And backwards prediction error is if we are using samples from the future, how well can we predict samples from the past? Samples from the past. And, samples from the future. How well can we predict samples from the past? There we go. That's what I was looking at the screen there for a second. Anyways, we're going to use these forward and backwards prediction errors. Oh, I apologize. That is supposed to be a plus, not a minus. We're going to use these forward and backwards prediction errors to find something called the reflection coefficient. This is sort of unique to the Berg method. And what we're going to do is we're essentially just going to take you've probably seen something similar to this in like an algebra course, but basically you're foiling out x plus y squared, right? And what you're doing is you're taking the middle term, 2x plus y, you're putting it in the numerator, putting the outside terms, because it'll be like x squared plus 2xy plus y squared. And you're putting them down here. And what that does is it creates a normalized assessment of what the different what our signal is doing when you move a little bit forward in time and a little bit backwards in time. And to give you like a visual on what I mean when I say that is, if we have like a function that, let's just say it's like little big, little, like that, right? Obviously trying to predict the signal at this particular point using signals from this particular point, isn't going to work very well. And so we're going to have like a very large forward and backwards prediction error, which is going to emphasize, I kind of want to keep that part, which is going to emphasize this particular area of the signal, which is important. Because what we're trying to find is what happens when the human voice has these big big changes like that, because what that means is the vocal tract that modulates to create these signals is also moving, is also changing in such a way that we're interested in. And to continue, this coefficient then is essentially a way to point out different particular areas on our signal that are important to us, and so that make the signal unique. There we go. That's how I wanted to finish that. Okay, now what we're gonna do once we have found these. Oh, this is a sample calculation down here that I did just to show you guys, like, okay, let's just say for our arbitrary numbers, let's just say our forward prediction error x is 20 and our backwards prediction error is minus 30, and that is y. And our if we run through like an example calculation of k would just be minus 0.9231. Just to walk you guys through, what that looks like for the first order. Obviously, what I want to also emphasize, I apologize for not explaining this earlier, is let's just say we wanted to calculate what's going on at pole 3. So when p equals 3. Obviously, because we're summing from 1 to 3, I want to use my little pointer, from 1 to 3, we are going to have like 3 different coefficients for pole 3. But then let's just say we go to pole 4, we're going to have 4, 3, 2, 1. Then we go to pole 5, we have 5, 4, 3, 2, 1. So you'll have pole 5, and then you can have like a previous coefficient of pole 5, which will just be for example, coefficient 4, coexample. Wow. I really put my words together there. Anyways, moving on. So this expression here, this is where it really comes down to, because what we're doing is we're trying to predict the coefficient of the next pole using a coefficient from the previous pole plus the previous coefficient of the previous pole, if that makes sense. And we're multiplying the previous coefficient of the previous pole. That I'm trying to underline. This means previous coefficient. This means a previous pole. We're multiplying this guy here by a reflection coefficient to essentially demonstrate to reconstruct that signal in a way where, okay, like let's just say there's a lot of forward and backwards prediction error. You're going to need more of a different part of the signal, right? So if we go back to an example, if there's a large amount of, forward and backwards prediction error, you're not just going to be able to use, the coefficient we use to go from here to here to get to here, right? We're going to need this guy plus this guy for sure to even try to come close to getting to this part of the signal, right? So from there, once we have all of our coefficients, we're going to construct our polynomial, and this polynomial is going to be in the z domain, which I think, yeah. So we're going to put a polynomial in the z domain, and sort of just like we did earlier. That's why I went back. Just like we did earlier with pre-emphasis here, what we're going to do is once we have our function in the z domain, is we're gonna. Or sorry, I apologize. Unlike what we did earlier, that's what I was trying to say, we're not only going to construct the polynomial, which is what we did before, but we're going to find the roots of it, which is something we have not done before. There we go. That's what I was trying to say. Now, the roots of a complex polynomial are complex. So, you'll have like z1, z2, z3, ... right? And actually not ... You'll have z1 through z5. If you have a pole value of 10, right? So if you have a polynomial of 10, if you have a polynomial of 10 to 11 terms, you'll get I should know this better, but like 4 to 5 different roots. And what we're going to do is, because they're complex numbers, they're going to have a phase angle. That's what this is supposed to say, this angle. Because they are complex numbers, they are going to have a phase angle. And what we're going to do is we're going to take that phase angle, we're going to divide it by 2 pi to sort of get like, okay, what is the ratio of this on the circle in radians? And we're gonna multiply it by our sampling frequency, because depending on what our sampling frequency is, your formants are going to be lower and higher. Just because that's the rate at which you sampled at. And this gives us our formant frequency. F1, F2, F3, F4, F5, right? And typically your F5 values are going to be your higher values, and your F1 values are going to be your lower values. Typically, your formants towards the beginning are sort of the more important, because like I said, I mean, while higher frequencies in the human voice certainly matter, a lot of what we do is in that lower frequency range, which is why like F1, F2, F3, F4 are the ones that matter the most. Whereas, you know, in F5, you can see some interesting changes, but you're also going to run into like a lot of null values. You know, obviously, like, you know, if I increase the pole value to 12 and I try to find F6, like, forget it. Like, the amount of null values I'm going to get there is worth a lot more than the pain of trying to find F6. So anyways, that is Formants.